coupling at both the positions, you get this compound. You can have the coupling at this position, you get this compound. You can have the coupling at this position, you can get this compound, which is what we desired. So I did the reaction for 65 hours, 150 degrees centigrade. I get a new spot, which is yellow in color. I isolate it, took the NMR, proton NMR, carbon NMR, and the mass. And from mass, the first thing I noticed is we don't have this compound because mass shows the presence of one bromine atom. This does not have any bromine. Now among these two, they have the same number of protons, they have the same number of carbons, and even in mass, they're going to show the presence of one bromine. So how do we distinguish them? Which is the compound? So first what I did was utilize our beautiful Chembra software to calculate the NMR. So this is the aromatic region NMR of this compound and this compound. They are in scale. And the major shift I find is as shown here as HA proton. This HA proton is ortho to a nitrogen and this ortho to an ester. Whereas this HA proton is ortho to an ester and ortho to a bromine. Thereby it becomes much more downfield shifted compared to this proton. I compared that with the NMR of my compound and I see the HA proton here. This HA proton lies close to this NMR, but still the other aromatic protons are completely shifted from this NMR. Right? So we still don't have an experimental evidence to suggest which is the molecule we are dealing with. One way to think about how to do this is if I have this compound and I go 2 steps ahead, this is going to intramolecularly cyclize to give me this helicity. If I have this compound and I go 2 steps ahead, this is not going to intramolecularly cyclize to give me this helicity. But if you know DV, it does not believe in anything more than a crystal structure. Right? So I tried a lot to get a single crystal of this compound. I was successful to get it in a mixture of DCM and hexane. So I loaded the crystal with the help of Chandra in our department and just kept my fingers crossed because my entire scheme depends whether I'm dealing with this molecule or this molecule. Right? And when I got the crystal structure, I was really excited for the first time in this project because finally I got something I'm proud of. Where I have the crystal structure, you can see the nitrogen here, the bromine here, and indeed the coupling happened at this PR. And I was amazed by the fact how regioselective this coupling is even at 150 degrees centigrade because we get the yield in 70%. So once we had this compound, our next step was to hydrolyze the ester to the acid group. And we could also get the single crystal of the acid and ethanol and water. Here you can see the acid groups, the nitrogen and the apical bromine. The acid was then converted in situ into an acid chloride in presence of thionyl chloride, which was then subjected to Friedel-Crafts acylation to form the helicity in the presence of tin chloride. The allyl ether was then converted to a phenol in the presence of aluminum bromide to give the racemic helicity with a phenolic group. So our next step was to dissolve the helicine into 2 diastereomers, and we did that by using a camphor and fluoride in the presence of DMAP, which is dimethyl aminopyridine. So even though these are diastereomers, theoretically you should be able to separate them in a column. But it's very important for the choice of solvent polarity used to separate this compound. So when I did this reaction and for the first time took the TLC, here's the TLC picture. I spot the compound here, I run it in 10:1 dichloromethane ether. I get 2 spots. From comparison, I know this is the starting material. Now, if I really make 2 diastereomers, I should have 2 product spots. But I have only 1 spot, and this is where a 2D TLC helps a lot. So I took the same TLC and ran it in this direction in 1:1 ethyl acetate hexane. And you see this spot splits up into 2 spots. Right? Now, and you also notice the lowest spot of the product has a very close RF to the starting material. The way we separate these compounds is first do a column in this solvent system, separate the starting material from the product spot, and then do a column in this solvent system to separate these 2 compounds. Alright? And then this is how they look. They look pretty similar, one orange, one a dark red in color, the upper spot and the lower spot. So far so good. But so basically we have a lower polar or more polar spot and less polar spot. Among these 2, which is M, which is P? That we don't know. Now, in order to know that, Thomas Cash from Columbia University studied a lot of crystalline camphonates, and according to him, the orientation of the camphonate determines the polarity of the molecule. So, if you take this camphonate here on a helice, the key angle which determines the orientation of the camphonate is the dihedral angle between the atoms 1, 2, 3, and 4. And I call that the alpha. For the case of M molecule, you can have two alphas. One is either 180 degrees or 0 degrees. To give you a better picture, I have here the Newman structure of the molecule. Where this carbonyl carbon is the front carbon, and the bridged carbon here is the back carbon. And you can see here, the angle between the red oxygens is close to 180. Similarly here, the angle is close to 0 degrees. Now among these two, which is the most stable orientation? The most stable orientation is the one which has the less steric hindrance between the camphonate methylene proton and the phenyl proton. So this one has a less steric hindrance compared to this one because it has a hindrance between the methyl protons and the phenyl protons. So if this is true, then our M molecule should have an orientation same as this particular camphonate. This is what I've drawn here. And if you notice here, the lactone is pointing downwards. Similarly for P, you have two orientations where you have alpha 0, alpha 180. And here are the Newman pictures of both of them where you have alpha close to 0, alpha close to 180. And among these two, this one is the most stable orientation because of less steric hindrance between the methylene and the phenyl compared to this one. And if you notice here, the lactone points upwards. And if this is true, then our P molecule should have the orientation of the camphonate same as this one. Right? Now, since the lactone points up here, this P diastereomer becomes more polar in the M, if you remember, which has the lactone pointing downwards. And so in the PLC, the lower spot is the P, which is the more polar spot, and the upper spot is the M. This is good now, but do we have any experimental evidence to show the orientation which we have proposed for the M and P is right? So if you take these two compounds, I've labeled the methyl protons in the camphonate ring as HA, HB, and HC. HA, HB, and HC. So if you see the NMR, this is the NMR in the alkyl region, and these are the peaks coming for the 3 methyl groups. When you see the HC methyl group, that is the one adjacent to the lactone, therefore it should be the most downfield shifted, and therefore this is HC. In the HB, both the HBs are pointing away from the camphonate, so this is the HB. Whereas HA in this molecule is pointing away from the aromatic core, whereas in this molecule the HA is pointing towards the aromatic core. Therefore, it gets shielded by the ring current of the aromatic core, and that's why it moves upfield compared to this way. But as I said previously, DB does not believe in anything other than crystal structure. The problem in getting crystal structure for these compounds is camphonate is a very bulky group. It does not like to pack. It's very difficult to get a single crystal of these molecules. So I tried a lot. It took me more than 2.5 months to get a crystal. For the first time, we have now a crystal structure of a chiral bridge trianohide with a camphonate on it. And this is the structure of the M molecule, which you would get from a binary mixture of hexanes and gelastase. If you compare the orientation what we proposed for the M, you see the structure is right on. Where you see the lactone pointing downwards, the methyls in the orientation which we proposed. If you also remember, the most stable conformation for the M is the one where the alpha is 180 degrees. And if you see the alpha here, it's 168 degrees, close to 180 degrees. Right? Now, once we have the diastereomers, although they are diastereomers, the chromophore in both these molecules is enantiomeric with respect to each other. So if we take the circular dicarbon spectra of these two molecules, they should be mirror images. And here is the CD spectra in dichloromethane, where the red curve is for the P molecule and the M curve is for the blue molecule. The blue curve is for the M molecule. You see they are mirror images. So our 2-week plan finally ended up to be an 8-month plan. But at the end of the day, we could finally, for the first time, selectively make epically functionalized chiral bridge triagonals. And I think that is what I like about research. When a plan fails, it gets a lot more exciting and you learn a lot more than if a plan would have worked the way you wanted it to work. So if you see the key accomplishment in this particular scheme is the ability to regioselectively couple the sterically hindered bromide over the sterically unhindered bromide, which led us to the synthesis of epically functionalized chiral bridge triagonal. The beauty of this strategy is it can be used to make even achiral epically functionalized chiral bridge triagonal. So here is the structure of the achiral bridge triagonal helicene with apical bromine group, which we could make in overall 70%. Now, once this epically functionalized molecules were made, it really opened up doors for chemistry which were completely previously ignored or were not possible. So if you have this epically functionalized bromine was utilized for a Stille coupling by a Stille coupling reaction made to a dimer, ethene-bridged chiral dimer, which was utilized by Austin from Professor Mike Bond's group for studying single molecule peroxide studies. If you're interested to know about this result, you can either talk to me or Austin. And for the first time now we have a chemistry to orient helicenes on a surface to measure their hierarchical response of oriented helicenes. So what we did was we took this molecule, did a Sravan reaction to install the aniline moiety, converted the aniline to a amide, which can now be used to do a thioline reaction to orient helicenes. The achiral molecule which we made, we did a Sravan reaction to make this molecule. And since helicenes are highly fluorescent, they can be used for sensing. And we were able to show this molecule can sense nerve mimics like DCP, which is diethyl chlorophosphate. Here is a picture of the sensing. This is a filter paper dipped in this molecule. And once exposed to DCP, you can see a nice turn-on fluorescence in UV. This work was done in collaboration with Professor Sravan Kumar at UMASS and Professor Abhishek Kumar from his group. So this synthesis of this molecule, epically functionalized helicene, now really gives an opportunity to make a variety of architectures. You can think of making molecules by head reactions, Sonavashira, Stille, any palladium-based chemistry reaction, copper-based chemistry reaction. So you can design a variety of architectures to study both the hierarchical response and the other applications of these molecules. Of course, this work was not completely done. I mean, I had a lot of help during this course of work. First and foremost, BV, for telling me it will be done in 2 weeks. For giving me the opportunity to work on this project. Professor Mike Barnes for the hierarchical measurements. Professor Schnar, who always kept his office door open for me to discuss the synthesis of these reactions. Professor Sravan Kumar at UMASS Lowell, with whom we are doing currently the sensing properties. Dr. A. Chandrasekharan, who helped me collect the crystal data for the single crystals. Dr. Piali, who was a postdoc in our lab and initially worked on this project with me. Austin from Professor Mike Barnes' group, who did the single molecule studies. Abhishek from Professor Sravan Kumar's group, who did the sensing studies. And the undergrads who worked with me during this project, Gayatri, Paul, David, and Ethan. Of course, the source of money was the NSF. But again, I'd like to thank the Research Fest Committee for giving me an opportunity to share my research. And last but not the least, the current and past members of the DV group. With that, thank you all for your attention.